Just says Cool. Well, welcome everybody. This is our first podcast. So I will caution everyone, this will probably be a little bit improvised. Something probably will go wrong because I break technology. But welcome to the first episode of Truth and Automation, the deep dive, which is Veritas Automata's podcast focused on deep dives into different technologies. Currently, we're going to be doing a series on ML and GenAI and the broader term AI. And with me, I have Saurabh. So, Saurabh, do you want to give your intro real quick and then I'll give mine?
Hi, everybody. My name is Saurabh Sarkar. I've spent most of my career building AI and database projects for transforming businesses. I worked with Ben for almost a decade, right? A little bit less than a decade, working on pretty interesting cutting edge AI solutions. We've been working on machine learning and AI before the AI and machine learning got that hype that it has today. So, I have a PhD as well in data sciences, and I've worked at JP Morgan Chase, leading a modeling team there as well. And prior to the PhD, I had a master's in robotics, working on autonomous vehicles.
Cool. So I'm Ben Savage, the CEO of Veritas Automata. I've got a mixed background in everything from supply chain and heavy logistics working at Maersk to a stint spent in consulting to the last, 17, 18 years in different startups, particularly focused around IoT and autonomous transaction processing of different forms. Where along the way, I bring a lot of technologies in because my focus in those businesses has been around innovation and helping people either disaggregate and disintermediate their existing businesses or figure out how to get ahead of their competition and do something new that no one else has done before. Saurabh and I love solving those problems that no one has an answer to. I think Saurabh sometimes gets tired of my late night or early morning white papers. I go, could we really do this? But for today, let's talk about, we talked about AI, and AI breaks down into really two big categories of machine learning and generative AI. So let's define those two categories. I think that's the biggest thing I see right now is people are going, AI, it's at the peak of that Gartner hype cycle. Everybody has to have it. They don't know what they need, but they have to have it, and they're very excited about it. So let's talk about what those two types of tools are, and then we can start to break down into some more use cases.
I'll probably give my 2 cents on what is the difference between machine learning and generative AI. So the best way to think about machine learnings are like custom built tools to do a specific task in a repeatable way, so that every time you send the same input, it gets the predictable output out of it. Whereas Gen AI is a probabilistic based method wherein the response from the large language models or the generative AI is unpredictable because it's sampling those answers based on a distribution curve. So it's a probabilistic. So those are the two big distinctions between between the two camps of what I call machine learning solutions, AI.
And so let's go into the machine learning a little bit more, because you described it as what most people think of as a simple algorithm or process.
Right.
But really, it breaks down into the data, the algorithm, and then what are you expecting do you know the output or do you know the input?
Correct. So, if you think about machine learning algorithms, yes, it is, driven by algorithm and data on it. But one of the key pieces in a lot of the machine learning algorithm is the data component of it. And if it has been marked as, target variables and what's not in target variables. So it is kind of tuning it and finding patterns to predict that output variable. That's the key difference between generative AI and machine learning, is that it is geared towards to do one thing and one thing really, really well. And the explainability of it as well. Like, how did you get to say your credit card transaction got declined? It's a typical example of machine learning example. The customer might be calling the customer, so why did you decline this? And ability to explain that hey, you have been all of a sudden you have been hanging out in Ohio and now you have a transaction like an hour from now in California. It's not feasible to travel that fast. How did that happen, kind of a thing, right? So that explainability piece of it comes with a lot of the machine learning world, and that's why you see that adaptation rate in enterprise is much higher for machine learning algorithms.
But there are some variations of conventional machine learning that are self-learning as well,
Yes,
right?
yes.
So how do you differentiate those from Gen AI?
I think you hit on a very interesting point. In the machine learning world itself, there's supervised and unsupervised learning. So supervised, the one where you have say that yes and no to certain different. Let's say you are doing a classification, whether it's this is a you're processing CT scan and trying to figure out if there's a cancer cell or
Yeah,
happening or not. So somebody has to build that data set on which that machine learning algorithm would be trained, saying that hey, these are normal cells, these are cancerous cells are something's happening there. So that's what we call supervised. So you're supervising it, telling it like a teacher what is good, what is wrong, and
yeah.
then the machine learns all the patterns that needed to learn to get to that
And you
information.
lock it at that point,
Correct.
right? So when you publish it at that point, you've
Mhm.
said, I've trained it on this known set of data, so I know exactly how this algorithm is going to respond every single time. It's highly deterministic.
Correct. And that's very interesting for predictability, where it's a system critical kind of solution where you need to perform in a predictable ways because
Yeah.
you have downstream processes. If it's predictable, it's not predictable, then the downstream processes also break. And that's where you see a lot of these machine learning algorithms being used in enterprise. Now the other set of machine learning algorithms, unsupervised. So think of again, the fraud example would be good. There are a lot of examples of what has happened in the past, the fraud patterns. You build a model on it. What happens when a new fraud vector comes in? It's very hard to detect those. In that cases, this unsupervised models comes to being. So what basically what it is, you're teaching the machine learning model with just the normal data, all the good transactions, which you might have like in large volume. So it picks up all the normal patterns, and as a new transaction comes in, it looks at the different patterns and says, hey, this is pretty much abnormal, I've never seen this before, let's flag it. And that's what we are calling unsupervised model. So it helps you build like a moat around your normal
Yeah.
transactions or normal population. Anything new strange comes along, you flag them and get a score around it, saying that hey, you got to do a manual inspection of that. So you know
Yeah.
um, the question you also asked is how is it different from the Gen AI kind of a setup. So Gen AI is more on you are feeding the just to step back on Gen AI is basically large language model. So you are feeding a lot of text and you're asking to predict what's the next text gonna be. And there's a probabilistic element to it, that while it is picking those tokens or the characters of the next word, it is doing a sampling based on what is the most likely probable thing to pick, and goes on and answers that. So as you can see that it is slightly different than
Yeah.
what we call
So you just hit on tokens and probability. So
Yeah.
let's I'll give a quick definition of how I think about a large language model.
Sure.
And there's really probably two main classes, three that kind of fit into generative. There's large language models, which are transformer based. There's diffusion models, which are more on image and video. And there's GANs, which are somewhere between that and conventional machine learning. For this, let's just say we're focused on the GPT
Right.
type solution, the transformers. When you think about that, one, they're all based off Bayesian statistics,
Mhm.
right? So that's
Yeah.
where those kind of things come from. But then when you talk about tokens, what a token is, it's a word or a set of words that they're now looking at what are the probabilities of what the next word or set of words is. So when you think about these tools, they're called a combination of autocorrect and search, right?
Mhm.
They're autocorrect in that they're looking at one or two words, but instead of one or two words, they're looking at pages and pages of data.
Correct. Yes.
And then they're doing the search kind of looking at that broader context as well, which is important when you think about it, because when you ask, why does a model hallucinate?
Yeah. So, you bring up a very interesting point, is that, when you are building, training some of these large language models, you feed in data, text of data, volumes of, like the chat GPT is supposed to be trained on entire written text, or a large portion of the entire internet out there. So when you ask an odd question to which it doesn't have a definite answer to it, again, it's a probabilistic based model, right? So it's
Yeah. So,
finding the most probable ones and trying to give you an answer. And
so if you ask it something it's never seen,
Yes.
it's going to give you an answer. It
Yes.
just may be probabilistically random. and what it gives you.
Correct. Your quality thresholds is way too low, and then it's giving you something which you think it's hallucinations happening, kind of a thing, right? So also keep in mind that a lot of these models are getting larger and larger, but also the context that's been throwing at it is also getting larger because it's pulling information from, and it may lose context as it goes along. So there is something called attention mechanism within the large language model. So it is paying attention to certain parts before it's predicting the next token. So that's a simplistic view on it, but often the answer involves referencing a lot of different abstract concepts and trying to combine them to come up with an answer, and that's where it starts to fail, or you see breakage as the scope gets bigger and bigger and starts to hallucinate as well.
Well, and I think I want to come back to that, why they break, or about the idea of concepts within that. But I think the other thing you mentioned early in the early piece of that too is you're talking about all the training data sets. I think one of the things that's important to remember is these larger and larger models are created. They're trained on every academic paper that's out there. They're trained on every Reddit post that's out there. They're trained on every 4chan post that's out there, and every other random thing that people find. So when you wonder why sometimes you get very questionable answers, there's a lot of people out there with a lot of free time to create things that don't make sense.
Yes. Yeah. I mean, that's one of these things that's plaguing large language model is the quality of data, because it's based on free-form data scraped from the internet or gathered from some other resources. It's not very well curated. There's a large amount of effort needs to be happening to curate that, make sure it's being taught the right things to predict a lot of this. And that's one of the challenges in the large language model. But again, it's very new, so
But I think that brings one of the things that you and I spent a lot of time looking at over the last year, which is this new idea of these small models that are a couple 100 million to maybe 3 billion parameter that are very clearly defined, so that you're working with a tighter set of responses.
Right. So that's the beauty of the smaller large language model, is that you can train them pretty inexpensively versus something like ChatGPT or one of the larger models. It takes like few thousand GPUs. Each of the GPUs is probably like $20,000-$30,000 worth, or even more.
It's more than that. I was just looking at some news today. I think it was in the Financial Times. So I think Microsoft had consumed 2 times more GPUs of like the A100 generation than anyone else. So they got like 425,000 some, and the nearest one was 200 and some thousand to them. So when you talk about, one, just cost, but two, just what do you need to go build those models? And most of that's going towards OpenAI capacity.
Correct. And one thing you should point out is that a lot of these models, even though they are trained on the large corpus of the world information out there, but for business application, you don't need that that big of a corpus to do it. But you still need that language comprehension piece of it, the logical piece of it. So there are a couple of processes or methods to do it. Fine tuning is one of them. You take a vanilla model and then train it on your own data sufficiently enough that it knows about your data and answer from that. That's one way to do it. It reduces the carbon footprint of using and training. And if every organization is out there trying to train something, the carbon footprint would be massive. And the expense wouldn't justify the purpose.
Well, and it's a several order of magnitude less level of technology you need to go and create that fine tuning. You don't need 400 and some thousand GPUs. You can do it with a couple that are reasonably achievable or accessible. And when we talk about those kind of smaller models, you're talking like maybe the Google Phi that you might be fine tuning, or one of the smaller Llama ones. And so those are super interesting when you think about it. I want to come back to one thing we mentioned before we kind of went down that track. When you were talking about the idea of how the large language models have a concept, and this is, I think, one of the key differentiations between conventional machine learning and large language models is we know large language models have those concepts, but they're not as easily traceable because of their sheer size as a conventional machine learning model would be.
Yeah, think of this way. Machine learning models like a typical, KNN or something like this, or even.
So what does KNN stand for those?
I'm blanking out on it. We gotta Google that, but I've used it way too many times. It's a kernel-based method, so you basically take your dimensional data and map it to a even
it's
higher
like a kernel-based neural network, right?
It's not neural network, but it's kernel-based algorithm, but what
Yeah.
it does, it takes your data and map it to a different dimension where you can say, let's say you have data which is very, very high dimensional data and you want to distinguish between good and bad, but that surface between the good and bad is very non-linear. So if you use a kernel, it maps it to a different space, and then you can draw a straight line or kind of straight line and kind of differentiate and then map it back. So that's the so the where I was going with that is with machine learning models. There's always a data scientist kind of cleaning the data, figuring out which
So
features are needed.
you're not using 4chan as your preferred
Yes.
training data.
Yes. So you're not throwing stuff at the wall and trying to figure out if it sticks or not. Machine learning models are built to be very, very purpose driven. So,
and that's one of the challenges too,
yes.
right? Is cleaning that data and preparing that data before you even train the algorithm.
Correct. Good way to think about this is the gold rush that happened some time back. It's AI is the new gold rush, right? Everybody during the gold rush went towards California. Some became rich, some didn't, right? So
is it gold rush or is it tulip bubble?
Well, let me stick with gold rush. Tulip bubble is the other one as well. But with the gold rush, AI being the today's gold rush, all of the companies are going there, hiring teams, and
buying and licensing data.
By licensing data, gathering all the tools, but not all of them know where to dig and how to refine the data. And that's where the core piece of it. You can throw the best algorithm at it, but if the garbage in, it's always garbage out. It cannot figure out what it is. So that's why the state of the AI is. There's a lot of hype around it. A lot of people are rushing towards it, but the key questions to ask is, what am I trying to solve?
So I want to come back to kind of where we were talking, because we got on a really interesting tangent there, so I wanted to let it run. But we were talking about kind of that difference between machine learning and the determinism that you can achieve with that versus the probability based of the Gen AI. And I think one of the things, because you and I've talked about this a lot, is there's no good, because one, nobody's evolved the tools, and two, because of the size of the models, there's no equivalent of a debugger or a stack trace, right? So if I go through a conventional machine learning model, I can step through it. I can see when I put that piece of data in, how it's triggering its decision. With the Gen AI tools, that there really aren't those equivalents yet. So you can go easily, particularly find where is this one particular concept stored, and edit it if it's incorrect, or understand why when you put the same question, maybe with a slightly different spacing, it responds differently.
Yes. So you brought up the concept, right? So with machine learning, the data scientists would try to inject those concepts into the model by training, by creating a flag or a variable saying that, this happened, I set a flag 1, and that's the input to the model. So what concept triggered when you are kind of tracing it back. But with large language models, since it's nebulous, it's picking up its own concepts, and it's very hard to trace them through the neural network itself, and not accounting for the probability distribution where it's randomly picking something out as well. That also muddies the water quite a bit on traceability.
Yeah, well, I think that creates the challenges we're all working with it, right? Because one of the things that we've both seen is you're working with a model and they put a new version out, whether they tell you or not. And OpenAI and some of the hosted solutions are probably more at risk of this than if you're self-hosting. But there's something that happens to the model, and in theory, it's the same version. You put the same question in, but something you don't know has changed, and you can get a fairly different response.
I mean, there are ways around it, but using vanilla LLM for anything enterprise is hard to do. I mean, it shouldn't be done. We have been working on a project where we would give references. Where did that pick that answer for? That gives you the citation kind of aspect to it. Think of this as more of a journal publication where you are claiming something, but you're also giving references. So those are couple of things, and then cross-checking those. So it can't, the entire pipeline of an enterprise LLM can't be like, I ask a question, I get an answer, but having checks and bounds in the place downstream and engineering those, and those need expertise and experience to build those systems up reliably. Is often you are making a decision based on an answer coming out of an LLM system. It has to be vetted before somebody makes that call. So
well, and I think particularly when you're using them in a corporate setting, in a business setting, that having those references to know where is the help manual it's pulling from, or where is the particular piece of corporate content it's pulling from, is super, super important. So it's not making things up.
Correct.
I think one of the things anyone who's worked with large language models has seen is that you will find cases where it's kind of like that teenager that you tell to go clean their bedroom and you go look in the closet and everything is swept under there and under the bed versus actually being cleaned up.
Yeah.
And it will make things up. I'm thinking of when we were doing that early experiment with agents last year.
Yes. Yeah.
And if you want to tell that story, because it was
yeah. So the agents is also a new concept.
Well, let's tell the story about where it went wrong, and then we can go into define agents.
Yeah. So we were trying to build a system where it would go and do some research on certain questions around it. So we'll set up agents. Somebody would go do the research, somebody would do the validation piece of it, and the agents could chat with each other.
And it looked like it was being really, really good.
Correct. And what we found out through the logs that it came up with answers without even saying did the Google search or whatever internet search.
It just made it up, right?
It made it up and said, hey, I did this search and I found these answers, and the rest of the agents agreed with it and ran with it and create a completely fictitious account of the report of what the questions we asked for. So yeah, this is where we got to have cross and bounds. And
well, you get the crossing bounds, but this is where let's go kind of backwards into what is an agent? Because I asked you the question before we got to the definition.
It ties with what you brought up earlier, the smaller large language models. So you could have multiple small agents or large language models specifically trained to do certain things. So and it could
so it could be just a really complicated prompt, or it could be a separate large language model.
Exactly. Or it could be a simple tool as well that could act as an agent. Something that does, some of these agents can go use a tool like a Google search or internet search, or it could use a tool which queries your internal database. It doesn't go out to the internet to do anything. Search, for example, if you're looking for certain financial number, it knows what tool to use to get those number and then compile that, because sometimes your questions have multiple layers to it, and agents are pretty good at breaking that and giving each of them to do certain things, gets all the answers back, compiles it in a nice little format which makes sense, and then produces the answer.
Well, and I think that's one of the things I do get excited about large language models for, is maybe not in and of themselves, but as the concept of an interface as a tool to go call other tools, right?
Correct.
That I think is really interesting, because now you can ask it that general question and it knows, say, hey, go look at this patient's CT scan, or go look at this piece of financial data. And then it can call a financial model or a image recognition model that is going to be deterministic, and it can give you that answer back. So you've got the ability to trust, but you've got that easy access.
Yeah, one more thing that comes free with this architecture is debugging. So let's say you got a bad answer from it. You can trace out through the logs which each of the agents did and got the information, and you can find, hey, this agent is acting funny. It's not pulling the right data for me.
So you know which agent went funny, but you don't always know why that agent went funny. But that's where you get the large language model problem.
Correct. I mean, that piece gonna be there until we solve the problem of how do we put the guardrails and it's staying within the bounds of it, and that's kind of goes into domain of machine learning kind of thing. But you still need the generative aspect of it to reason it, right? So, but how do we make it reason within? Think of it like a teenager, right? With a attention span of a goldfish or something like that. This is shiny, it goes there, and it could be completely driven by probability distributions, and that, hey, it goes down a completely different path. So the core problem to solve is to create that whole guardrails around the LLM so that it doesn't go where it doesn't need to go, kind of a setup.
So you kind of mentioned back and brought us back to conventional machine learning. I know a lot of what you and I've worked on in this, just with the projects that we've been applying to, have been around image recognition.
Yes.
But we've talked about other pattern stuff. What are some of the current trends in conventional machine learning, and some of the new things that are coming up that people might not be as top of mind about?
So one of the things I'm seeing quite a bit getting merged is the generative AI producing data for machine learning application. One of the biggest challenge with machine learning is getting clean data or even synthetic data production that kind of mimics what a real world would look like. And a lot of these generative systems can produce that. An early example would be GANs-based systems. So you feed in a data from, let's say, a gearbox, vibrational, and all of the current data, and let it mimic that and produce a large amount.
So again, as a generative adversarial network, where I have one network that's generating data and one network that is validating that data, and they keep just doing cycles until they can fool each other, basically.
Correct. Basically, they are two little AIs, or they are fighting each other. One is trying to con the other, and the other's job is to distinguish between real and the artificial data, and over the time the generator becomes so good that it cannot distinguish between real and old data.
So you mentioned that under the class of generative networks, and a lot of people are going to think about like the fusion type models, like Stable Diffusion and
Right.
Midjourney and all that.
Yeah.
So this is when you're talking about using data to enrich these algorithms, you're particularly talking about GANs more so than those, or are you talking about both?
It's the same family. So if we are doing something like a tabular data, that generative AI would make more sense. But if you're thinking of trying to train an autonomous vehicle and have some of these image or video generating models
Yeah.
produce situation wherein you create kid running across the street, all of a sudden you put in that input, create a nice video, and let's see how your model performs in that outlier case, because it's very it's hard to stage those things and find those data.
Yeah.
But having a generative do that for you, you could create distinct advantage.
And we'd really prefer to train on synthetic data than training on kids running across in front of autonomous vehicles.
Right. Underneath, this all sounds cool, but there is a whole layer of data checking and sanitation that needs to happen for any of these to work. So a very typical example that came out a couple of years ago was, a model was trained to distinguish between horses and dogs, and it did really well in the training data. But in the real one, when they would kind of mix each other. So when the scientists went back and looked at it, they found that the horses always had fences in the background, and the model picked that up, not the
Yeah.
horse, because and so again, this is where it comes down. It's not a magical box that you touch everything and the problem is solved. It needs clear thinking, problem definition, and making sure the data is good before the model is trained.
Well, and I think that's the one thing people don't always think about with machine learning. It will sometimes pick up on things people don't see,
Right.
but you can still figure out what it is queuing on. And
Mhm.
that's important a lot of times, because if it queues on the wrong thing, if it queues on the fence in the background and not the actual horse,
Yeah.
well, you've made a really good fence detection algorithm, but not a good horse detection algorithm.
Exactly. So that's going to be an challenge across all the enterprises. How good is the data? It's not the most glamorous piece of the whole pipeline of building AI system, but it is one of the most important aspects of it.
So I'm going to jump back to generative AI, and I'm going to apologize to everyone if you haven't picked up that I have a little bit of ADD. So we're going to bounce around a little bit in these conversations. But we started talking about fine tuning,
Mhm.
but there's another technique that's related to it, right? There's the retrieval augmented generation, right?
Right.
If I don't reverse all those words.
Yeah. So that's a very, very interesting, where you are feeding. So everybody has used ChatGPT today, right? So when you're asking a question, but when you ask a question, if you also put some context around it, saying that, hey, these are some of the references or the material, and can you answer based off that? It gives you a different answer than just asking a question. And that's what it is. What you are giving it more and more context to it. So how does this work for an enterprise setting, right? So a lot of this large language model hasn't seen your data because it's kind of proprietary data. But
And you want it to remain proprietary.
exactly. And you don't want to put that out there in the world for people to train and get your trade secrets or whatnot, right? So the way you would build a system like this is to build a pipeline. When you ask a question, it goes back and looks at your document using, again, part of embedded systems where all the text is converted into a vector, and then
Embedding systems, not embedded, not IoT embedded.
embeddings basically. So you would pick on materials within your knowledge repository, then find the piece which is relevant to your question and bring them up. And then the LLM takes the question, looks at all of the context brought back, and only answers based on that. And then this is what it's called RAG. So you are not fine tuning it, you are not making it go through the hoops. And since you are providing the references for it to answer, your answers are more grounded. It's not hallucinating right off the bat.
Well, and I think it gives you a couple other advantages too, right? One is you don't have to spend the time doing the fine tuning of the model. Yeah. But the other, and maybe more important in some scenarios, it does give you some different security options. Yeah. Whereas if I fine tune the data in the model, anyone who has access to it can get access to those answers. Absolutely. Whereas if I use retrieval augmented generation to do it, now I can start to have someone check and say, do they have permission to even see this data before I surface it to the user?
Correct. I mean, that would be tremendous for the enterprise world, wherein you have access control on all your knowledge bases, and having that access control pushed up to the retrieval piece of it helps quite a bit. And you can build in a lot of checks and balancing that, hey, I couldn't give you an answer because you don't have any context or
Yeah.
something like that. But yeah, it's a very interesting direct application of LLMs in the enterprise well without training or fine tuning any of the models for sure.
Well, and I think you kind of hit on the other piece too about the ability to manage the context, right? I think that's one of the things. Every large language model has some different either inbuilt responses or context or guardrails, and they're all a little bit different from the models we've seen. I haven't seen any two that are going to respond exactly the same. Even when you look at models in the same family, like if I look at the llama family, I can ask the same question and I will get different responses based on their guardrails.
Right.
And I think so that's important for people to think about when they're selecting a model, because some models are going to be more adapted for certain kinds of answers, and some will have more guardrails. But then as you go implement this from a business perspective, you need to think about what are those contexts that you need to put in. Like we were doing some work with FDA clinical studies, right? And we discovered that you could get it to give the summary of the study in the lyrics of a rock song. Entertaining,
Yes.
but maybe not the right answer for that.
Yeah.
I think the same thing goes with conventional machine learning, right? You've got to choose that right algorithm and right tool set to the problem you're solving.
Right. Yeah. I mean, it all comes down to, defining your problem properly and, knowing the risk and what data you're feeding into the system is going to be the key point behind success of an AI solution. It's not a magical wand that you shake around empty ball and disappears. There's a lot of work that's not seen or, not highlighted in a lot of the media today, but there's a lot of work that goes behind the scene to make that work.
So you could create a hell of a magic 8-ball with a large language model.
Sure. And it could, convince you to keep on playing too. We have been talking about that earlier as well.
Yeah.
But yeah, I mean, if you think about AI, it's a great calculator. It can do the math really well, but it doesn't know why you are doing certain calculation. And that's the human piece of it, because we got to make sure that human intuition is always in the forefront. And the problem you're trying to solve is very well defined before we can bring in the AI or any other solution. Because often problems can be solved without machine learning and AI. It could be a simple logistic regression kind of solving it. If that's the case, solve it that way and then save the resources for more difficult problems too.
Well, yeah, it's you save the resources, whether it's time to develop the algorithm or compute and computer needed to go do it, or just the time, the risk.
Yes.
Right.
Yeah.
So all three of those are things you need to consider.
Yeah.
So I think we're going to wrap this up for today. We're at half an hour. This is going to be something that we do, let's call it 2 times a month. I think this is the first. You won't see another one in December because it's already almost Christmas, scarily enough. But this is the Veritas Automata deep dive, and we're diving into technology to see how deep we can go and what we can help people understand and our potential clients and partners and friends. So I think the next one, I think we'll probably talk about some more examples in both the machine learning and GenAI, or at least the GenAI perspective, and look for that next one to be scheduled in early January. If anyone listens and has any questions that we can answer, feel free to reach out to us. And we're glad to either help you with your conventional machine learning or your GenAI or other creative problems that you need help solving. Saurabh and I don't like to be bored.
Yep. Yep.
Cool. We appreciate everyone.
Thank you. Okay. Not too bad. We winged it.